Hi, everyone. Welcome and thank you for joining today's webinar. Blending is never as easy as it first appears. My name is Julie Chenuin, and I am your facilitator. With me is one of our most popular guest speakers, Dr. Willie Hendrickson. He is the founder and CEO of AVEKA, the president of the International Fine Particle Research Institute. He comes to us with a wealth of knowledge in particle processing and really an extensive experience from the business commercial standpoint. Our group is super honored to have him, and I will be happy to share other links from his previous talks. But for now, I think it's time for me to hand the screen over to Willie. So Willie, whenever you're ready, please share your screen.
Well, welcome everybody. I'm glad that you're here. I'm going to give a talk on blending. It's never as easy as it first appears. It turns out that I put this in here because it really isn't as easy as it first appears. And in fact, when we sent out the first announcement of this, I think it actually listed appears as a mistake instead of appears. And I thought, well, maybe I should actually change my talk to that because it was surprisingly appropriate. Let's get going on with the talk, and let's first talk about the outline. I'm going to give you one slide about AVEKA. I'm going to give you one slide about particle processing, what I call the big six. And I'm going to get really into the nuts and bolts, and that was an intended pun. We're going to start talking about Brazil nuts and powdered sugar donuts, how it relates to blending. We're going to talk about some blending methods, just powder flow and Derek Geldart and flow fluidization. I've got lots of examples to talk about, some opportunities at the end and conclusions. So let's get going with this talk, and hopefully you'll find it as interesting as I did to actually put the talk together. So just a short overview about AVEKA. If you don't know, we are a particle technology company focused on contract manufacturing. We spun off from 3M in 1994, and we are comprised of 5 separate companies with 290 employees, and we do just about anything from food to chemicals to cosmetics and lots of stuff in between and beyond. The talk, since we are a particle processing company, we are always focused on, different ways of doing particle processing and understanding particle processing. And I call these the big six. There's probably a big 36, but, just for this talk, I would say that things that we all are interested in particle processing range anywhere from how do we characterize it to how do we agglomerate something to how we do size reduction. But today, I'm going to be focusing on the blending part of the big six. And if you look up on the pictures that I have there, one of the pictures is a picture of gunpowder up in the upper left-hand corner of the pictures. And that's clearly a blending process, but it's also a blending and an agglomeration process. So, something as simple or perhaps as complicated as gunpowder uses blending to get the final product, and without the blending you wouldn't have a product at all. So let's talk about Brazil nuts. And Brazil nuts and powdered sugar donuts, they're all about we've blended something together and now things can start to happen. And so this is what we're trying to do. We're trying to take a blend, and let's focus on Brazil nuts to start with. A mixed nut blend, as you can see in this picture. And one of the interesting things about Brazil nuts, and one of the interesting things about particles in general, is when you have a collection of particles, and you can see them down here in the bottom where you have numbers of big particles and small particles, in the process of shaking those particles, the Brazil nut or the big particle will always rise to the top. Now, this is quite surprising because your first intuition would say that that big particle would sink to the bottom, at least if the density and the like was the same in fluids as it is in particles. But in fact, we can go to a lot of trouble to blend particles together, and we can end up, after we blended them and they're moved across the country or used in your factory, you can actually end your good blending process fall apart, and you can end up with those big particles on top. And so one of the issues that we're always thinking about when we're blending is how to avoid this Brazil nut effect. Powdered sugar donuts, I'm a big fan of powdered sugar donuts. I've loved them for years. And when I go to the county fair or the state fair, one of the things that I see is I'll buy a bag of powdered sugar donuts. And it's really a blended process, right? I mean, you have two particles in there. You have the powdered sugar and you have the donut. And realistically, the blending works by the powdered sugar or the sugar or whatever it is sticking onto the donut. But at the end of after you've eaten your donuts, other than the fact you've got them all over your shirt and your fingers and everything, if you look at the bottom of your bag, you'll always see powdered sugar at the bottom. Now this is a type of Brazil nut effect, but you know you can see all these small particles go down to the bottom. So your blending process, your coating process didn't work exactly the way that you wanted it to do. These are some of the challenges that we have after we do the blending, but what are the challenges that we have when we do the blending itself? So I have a picture here with the discussion of what conditions should you use in blending. This is a report that was written by a man named Fernando Muzio and his graduate student Shinbrot in 2001 and published in an IFPRI paper that shows what happens when you set up a cone blender with some dark, smaller beads, and these are big beads, relatively speaking, 1.6 millimeters, and some large white beads, still, you know, big compared to maybe a fine powder blending. And what he did is he put them in a cone blender and he set it up where the small particles were on the edges and the large particles were in the middle. And he started rotating this cone and then would take a picture every few revolutions. Now he was doing a relatively high rotational speed. And what he got rather than blending was he got consistent movement of the particles to the center of the cone, as you can see. He didn't really get blending, he got movement. Interestingly enough, if you stopped halfway in between, like maybe on this center picture here, and you slowed the blender down, the particles went back out to the edges. His paper dealt with a lot of why this happened and the theory and the calculations. But for us that are practitioners, the important part is just that this can actually happen. So changing the blending conditions can be an incredible factor on this. I'm not going to give you all the answers today. I'm probably hardly going to give you any answers today, but being aware that you can change your conditions, and whether it's the rotational speed or the type of blender that you have or the type of materials or the time or the intensity, all can make a big effect. And we need to actually pay attention to this as we're going through and doing blending. So the blending whys and challenges. Why does anybody do blending? Well, it's probably to improve the final product uniformity. That's probably the basic thing. So you can get everything kind of uniform as you take samples out. You can have the same product. It's to create a new product with multiple components. And just look at the sample down here of mix. You know, it's got a lot of different particles in there. I mean, different sizes and shapes, all kinds of different ways. And if I put them in separate bins, it wouldn't be nearly as enjoyable as having that product all mixed. I'm going to show you a way that blending can help enhance reactions later on. And there's a lot of blending that's going on just to improve the powder flow. Can we put a flow aid in there and can we do it? There's probably another 100 reasons why you're blending. These are just 4 to kind of think about as why you're going to do this. The challenges that we have over here can you know kind of mimic why we're doing this. You know, can we get that uniform product? Do we have segregation that, like Fernando showed in that previous slide that I have? If we do this wrong, we'll have particle breakage or we'll have particle agglomeration. And I'm actually going to show you one example where one of the challenges was we had a blending process that ended up with a lot of micro growth. It wasn't with a bread sample, and I swear to God, if you ever see bread that's turning blue, run away from it. But you know, this idea that things can happen in there that you wouldn't think about are always important to be thinking about. Now, this slide here, these are some of the blending methods that you can use, and by no way are we going to go through each and every one of the blending possible methods that there are, but I picked some really standard ones that people use. Probably when I think of blending, I always think of ribbon blenders, where you have a chamber, you have mixing paddles or ribbons within here that can blend up your product. And boy, this is kind of a standard way of doing blending. I would say another standard method of blending is the V blender shown here on the right in the middle of the slide. I mean, this is a great blending process. But you know, there's lots of other really interesting ones. There's a blender called a Forsberg mixer. So these first two blenders might be more gentle mixers. This is a high shear blender. These paddles are moving at high rates, and you can get some incredibly good blending in this process. This is an example of a plow mixer, where instead of having ribbons in here, you have plows that move the material around. Here's an example of a paddle mixer. And I've even put a fluid bed coater dryer in here as a mixer, because I'll actually show you an example later on. And these are great methods for doing blending. There's tons and tons of others. Let me give you a few of these others, because these would be what I would call really different blenders. And we'll talk about some of these later on. So this is a picture of a spray dryer, and here at AVEKA, there's many times that if we can dissolve materials together and spray them out, that's a great way of doing blending, because we're now calling on solution blending. It's a way of ending up with a dry powder blend, just a slightly different way. I'm going to talk a little bit about a magnetically assisted blending process that I was involved in inventing when I was at 3M many years ago. Those of you might recognize the Resodyne acoustic blending system from a lab standpoint. These are incredibly great mixers. This is an example of a centrifugal mixer. Commercially, it's called a FlakTech here in the United States. This is one of the better mixers for a lab mixer I've ever seen, and we'll talk about this a little bit at the end. Here's a tumble mixer where it actually has a spray bar in there. So basically like almost like a clothes dryer where the particles are tumbling, and you can spray, or you can just use it as a mix. And you know, to show you that for somebody like me who's been in this business for almost 36 years of doing particle processing in one way or the other, even an old dog can learn new tricks. And as I was getting prepared for this talk, I found this funnel mixing setup that I actually have listed as one of our examples. And we'll go through here how 3 simple funnels can be a great way for blending. And once again, I've given you some examples here of blending methods. What I haven't given you is the universe of blending, and I'm not even sure where you would go and find that. Some of the ways you just are going to have to take a look yourself, but these are some great starts. But the question that always comes up is, what blender is the best blender? What blender is the correct blender? A friend of mine that I know in IFPRI, that's part of IFPRI, Jeff Hoffman at Paul Abbey, has put together a list, and he's got a much more extensive list than what I've taken here. But I've looked at one of the ways that he looks at which blender to have is, what's the maximum density of the material that you can actually put in the blender? So things like ribbon and paddle blenders, these are relatively low density. I mean, this is the maximum density that you can have. But other blenders like double cone blenders or V blenders, that can put some pretty heavy ceramics, metals in there for doing blending. So one of the ways that you might pick which blender that you want to use is how dense your material is. So the answer is you can probably use all of these for low density blending, but you sure as heck wouldn't try to put metals into a ribbon blender, because you'd probably break it. I mean, they just don't move. The other thing that Jeff talks about is, so you've got a blender. How can you get the maximum capacity out of a blending? Because at the end of the day, you want to get it in, you want to get it out, you want to get it mixed, and you want to get on. So he has a listing that once again I've kind of cribbed from here. That if you have a lower density, you can get a higher capacity. If you have a nice sphere particle, you can get a higher capacity, as opposed to fibers or blocks. You don't get nearly the capacity in the system. And I like the one that he had down here where he talked about if you have low moisture, it's usually you can get higher capacity. If you have high moisture, you're literally blending slurries, you can get high capacity through your dryer. But if you're in the middle, lo and behold, it can actually block the particles together. So a small amount of water is okay, a large amount is okay, and you get in the middle, and it isn't just fine. It's the worst that you can possibly have. Now, picking that blender, having that opportunity to pick that blender, that's usually something that we all have the opportunity to do when we're building a brand new facility. But like most of us are faced with the processing dilemmas of what do you have? So I call this the available equipment dilemma. Uh, if what you have in your lab or what you have in your production plant is a ribbon blender, guess what? That's the best blender that you can possibly use because it's going to be the one that's available to you. By the same token, uh, if you have a scalability issue and you have a ribbon blender in your lab, but you need to get to a high volume, maybe the ribbon blender isn't going to work. The classic example of this in the lab, when you're doing distillations, you might use a little setup like this, and you can almost hold this in your hand. But if you're out in production, they don't even look the same, and they're 100 feet tall. So these are processing development dilemmas. But this one for blending, it's what you have available 9 times out of 10, that's what you're going to end up using all the way through your process. It might not be the right process, but that's what it is. The last thing I want to talk about before I get to my examples is we are really talking about powder flow. And if you don't understand powder flow and an example of one man's attempt to classify powdered flow, this is a Derek Geldart particle classification. This is almost standard for everybody that's working with particles. He classified particles based on the density of the particles and the size of the particles, and he found that the powder flow, whether it's just flowability or fluidizing ability, really had a dependence on these two factors. The problem particles that we all worry about are group C particles, and this is an area that we're almost all working on. The particles that seem to flow the best are these group A and group B particles, and then group D particles, they're just big particles that sometimes can have challenges in moving because they're so big. But you will need to know whether you are working in that cohesive range or you're working in that granular range, and are they flowable, because it will have a tremendous effect on how well your blending actually goes. So blah, 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 blah. Let's actually look at the examples and see what we've found out about particle processing. Now, the first picture that I have here, this is a great picture of monomodal particles that we've made in one of the projects that we had many years ago. And what I like about this project in a mixing talk, there is no mixing needed because they're all the same. Whatever sample I take, they're going to be the same. In the 27 years that we've had AVEKA together, this is probably only the second time we've ever had that experience. So I've got 2 instances out of thousands where I didn't need blending. All the rest of them I needed blending. What I'm going to talk today about from the example standpoint is I'm going to talk about the standard blendings, and these are pretty boring, but they're interesting to talk about from a why did we pick what we picked. I'm going to talk about a blending gone way bad and why it went way bad. I'm going to talk about some clever and unique solutions. Not all of these are things that we've done here. A couple of them, the trituration and the funnel flow, these are examples from other people, but most of them are things that we've done here. What I'm going to do in each one of these examples is I want to talk about what is it that we are trying to do? What is it that we need? How did we approach the problem? And why did we pick a particular blending method? Once again, this is not going to be an extensive list of every problem and way to approach a problem, but it's going to give all of us some ideas of what might be the best way to consider blending and how to approach it. So let's talk about the easiest of the easiest. I'm going to blend using ribbon blenders. I'm gonna blend food powders. It could be some starches, some yeast, some dry flavors. The particles are pretty much the same size. I mean, there are clearly examples where you're using ribbon blenders where they're not the same size, but for this one example, I'm going to have everything about the same, and I don't really have any special requirements. I don't have a a micronutrient in there. I don't have to add water. I'm just going to put it in. And in fact, the picture down here at the bottom shows somebody just standing over the blender, emptying a bag of powder into this ribbon blender, and he's going to put 4 or 5 more powders in there, and he's going to actually get a blend. Turn this on. The challenges on this thing are it's pretty straightforward. We pick a time that might be anywhere from 5 minutes of blending to 20 minutes of blending. This is a pretty standard process for food materials at AVEKA. It's easy. It's also we do industrial materials, but in this example here, I'm just talking about food materials. The reality is that the biggest issues that we have on using these types of materials is getting the product into the system without making a dusty mess and making sure that the formulation is right. And not because the formulation hasn't been designed to be right, but when you're taking lots of different materials, the reality of this is it a mess because how I'm putting it in, and did I get everything in there? Now, I would like to say that no one that's ever done blending in a manufacturing process has ever made a mistake in the formulation, but I think we know that that's wrong because it does happen. And no one has ever had a problem getting particles into a process without making a mess. And that would be wrong also. We use some bag dump stations, and I think these are pretty standard. So, you can pick just about any blending process, but you're going to have to get that powder in and you're going to have to get it out. Typically, these aren't big problems. And if you have the right equipment and you really set up your formulation system right, I mean, this is protocol and process, should be actually fairly easy for you. But what about using not a ribbon blender, but let's use a high shear mixer. And this goes back to that Forsberg mixer. The reason that we were doing this, the challenge was high volume mixing. This process does have the ability for liquid addition, and post drying might be required, but let's just consider this if this is just high volume mixing. This Forsberg mixture that I'm showing you here is probably about 2 feet across, and it's probably 2 feet wide. It can do up to 5,000 pounds an hour and give you a great mixer. So what happens is these paddles here are moving rapidly. You've got 2 sets of paddles. They intermesh very nicely. And if this is a continuous process, this is actually a batch process shown. The powder comes in at this end and the powder is moved down to this other end, and the powder leaves from the bottom in a continuous fashion. This is a type of process where you're going to set up on a big scale, 5,000 to 10,000 pounds. I mean, you can really get some large volumes through here. We love this process. I mean, this is a great process if you're doing that big volumes. Typically, a good example where something like this might be used is in the formation of granulated soap powders. I mean, this system will also do some agglomeration, but there's big volumes that have to have the right cost, and so we don't have time for loading up systems and unloading systems. It needs to be continuous. What went wrong with this system for us? We actually put this system in our plant and it works fine. I mean, we didn't have anything wrong, but just like the other process that we have in process, we really have to be careful about how we're adding the materials, how we're handling before and after. And if we are mixing with agglomeration, many times the yield can might be only 60%. So there's a recirculation mode. Now that's not typically what we think about in blending, but if you start mixing blending and agglomeration and drying, you can actually have some issues where you're going to need to recirculate your materials and make sure you get everything done right. The third relatively easy process that we looked at was blending of a very dense material. It was a ceramic material. Some of the examples are shown up here. These can be silicon carbides, these can be aluminas, they can be metals. We typically don't do metals ourselves, but they have that high volume and or high density, excuse me. You can't do these materials in a ribbon blender. You would break your ribbon blender. So in our particular case, we actually went to a V blender, and you can see one down here at the bottom. This is relatively speaking, a small production V blender. That's about a 10 cubic foot V blender, but they come in smaller sizes. Here's an example of a lab system that is made out of plastic, so you can actually watch to see how it goes. It's a great system. These systems aren't expensive, and interestingly enough, you can see a bar just barely across here. That bar can be used for liquid addition, so you can blend a powder or a variety of powders, add liquid to it, and the system dumps out nicely, and it's nicely scalable. It's a great process to use. And once again, just remember, even though we're using it for this high density material because this is what we needed to use, we could have just as well used this for lower density materials also, and we have. Well, what went wrong? What can go wrong in a system like this? We have seen some cross contamination issues, and we've seen premature dumping issues. So once again, let's go back and take a look at this picture here. You're loading the product up here on the top, and typically you're unloading it at the bottom. And there's been many times that people, not many times, I should hesitate on that. There have been times that people haven't actually closed the bottom, and will end up dumping the material all over the place. That's a bad day for everybody. How do we solve the issues? Because the blending is absolutely straightforward. It's really quite nice. How do we solve the issues? It's all about protocol training and PM maintenance. But that's just standard manufacturing operating procedures for everybody. I think that this next example, blending gone bad, is really a unique and interesting story. So let me tell you, let's do the statement of the challenge here. I wanted to add a small amount of water to a dry food product. Now, I want to go from about 1% up to 5% moisture. I'm going to use a ribbon blender. I'm going to use a spray atomization. I'm just showing here a tumble coater, but we could have easily used a tumble coater because I wanted to show the spray atomization. The result is it worked out really well. The PSD changed slightly, just showing a particle size distribution. There apparently was just a little bit of water, the swelling of the particles. And as far as we could tell, we hit a home run the first time we ran this product. It worked perfectly, except what went wrong. So two parts to this one. The blending was easy. It was straightforward. The problem was everything went wrong. There was incredible microgrowth afterwards. Now, if you're in the food business, you know that 5% moisture is not a bad thing to have. 5% moisture, you shouldn't have microgrowth. And in order for you to have microgrowth, you typically need three things. You need food. Well, we're working with food. You need water, which we just added to food, and you need a source of the microbes. Now, we didn't add enough water to cause a problem, and yet we had this problem. So the first thing that we knew that there had to be microbes either in the system to start with or added in the water. And we were actually able to easily prove that the water wasn't the problem. So the microbes must have been there, but they weren't growing at the low percent moisture. The question is why did they grow when we were still below what would be a reasonable number for moisture in the system? We believe, and this is probably absolutely true, is the water wasn't uniformly distributed. There were wet spots that were higher than 5% moisture, but overall the sample was 5% moisture. Now let's think about this. This is the classic issue in blending, is your product uniform when it comes out? If we go back to a Chex Mix type of scenario, or mixing cereal, you can usually look at it. You can look with your eyes and see, yep, it looks pretty uniform to me. But when you're adding something on the micro scale, it's incredibly hard to tell. And in fact, we wouldn't have known if this had been adding water to alumina, we wouldn't have been able to tell what happened. But because we had a micro contamination that we actually got from our customer, we were actually able to add water. We could then, determine that the water wasn't uniformly added to the system. The wet spots in there allowed the bacterial to grow, and this was a real challenge. And I think this happens. This inconsistency of mixing happens on micro scale all the time, and it can be incredibly difficult to figure out. Bacteria worked pretty easily for us to figure it out, but it wasn't something that we were pleased with. We actually easily solved this problem by adding a microbial kill in the water. So when we put it in there, the bacteria could start to grow and then die. But from a blending standpoint, I don't think we ever solved the uniformity issue here. So let's talk about blending the micro ingredients. This is now we're into the what's a unique way of doing it. The question is how to blend a small amount of a micro ingredient in a large batch of a functional ingredient. And this is work that was done by Alice Wilkinson at Watson. And this is her data where she talked about adding vitamin B12 to a blended mixture, and the recommended daily amount was only 6 milligrams. She did a nice calculation that showed that each 100 mesh particle weighed about 1.2 micrograms, which means that in an average serving, she only wants 5 particles. So here's her blend down here at the bottom. I mean, there's the white particles are the carrier, and the red particles are the blend, excuse me, the vitamin B12. And it looks like a fairly uniform mixture. The question is do you feel comfortable about this micro ingredient being so uniformly distributed that you will actually get 5 particles every serving? And in the case of the work that was done by Alice at Watson, they didn't feel comfortable about this because there's going to be enough variability how you pull the sample out that having 1 or 2 or 3 or 4 or 5 particles in a sample is going to give you something that, even though it seems uniform, you could not uniformly sample. It'd be very easy to ununiformly sample and get a recommended daily amount not properly. So what Alice did is, I think this was brilliant. She did what's called trituration. She actually dissolved the vitamin B12 and sprayed it on the surface, and you can see the difference between this uniform and this uniform blend. And this was done by a fluid bed or a spray drying process. I consider that in this case, Watson and Alice Wilkinson came up with an incredibly brilliant solution to blending uniformity. So what they sidestepped this mixing challenge of micro ingredients by dissolving it and actually spreading it out and then drying the product. I don't know, is that cheating or is that brilliant? I would truly consider this brilliant. Let's consider another challenge that people have is if the particles are the same size, like the original ones that I showed back there that were monodispersed, blending isn't needed. But when you're trying to blend large particles with small particles, you start getting into this Brazil nut effect or the powdered donut effect. And so we had a question that was asked many years ago about putting fumed silica to improve flow onto powders. The process needed to be continuous, and it needed to be stable. And why did it need to be stable in this mixing? So we didn't have all the flow aid fall to the bottom of the bag like the powdered sugar does. The way that we approach this problem, and this was a problem that we were working on when I was at 3M actually, is we came up with a completely different mixing method that we call magnetically assisted impact coating. And we're going to measure the process flow, and we're going to look at some mechanism here. But let's take a look at what this process actually is. So this is a continuous process where we have a tube. This is like a plug flow reactor that's nested in a magnetic field that we apply an alternating current on which we produce a oscillating magnetic field. We set a number of screens in this system, and on top of the screens, we put permanent magnets. The magnets are sized so they don't go through the screens, but the small particle and large particle that we're actually putting into the system will go through the system. When we turn on the magnetic field, the magnets oscillate. They look like Mexican jumping beads on speed, and they literally pound the small particle onto the large particle, kind of like the micro concept of powdered sugar donuts. And we come up with this coated stable particle, as you can see at the bottom here. We compared this mixing method to the standard mixing method of V-Blender, and then we measured the flowability of this ensemble using FT4 from Freeman Technology powder rheometer. So the results that we got are shown here. This is an example of starch particles that were coated with fumed silica, and what you can see is the fumed silica decorates that starch particle, dramatically improves the flowability. You know, it's kind of like that powdered sugar coating, with the difference is that the fumed silica in the mace processing stays on the particle, whereas it would fall off in a ribbon blender. So we looked at the basic flow energy, and just so you know, from a Freeman Technology standpoint, basic flow energy, the higher the number, the more cohesive or less flowable the powder is. And if we're trying to make this more flowable, what you can see is that raw powder, whether it's starch or citric acid or mineral abrasives, you can see it starts up high and it goes down very rapidly. And so these low numbers mean that you have a very flowable powder, and your high numbers mean that you have a cohesive powder. And if we actually compared the mace system to the V-Blender, you can see that the mace system has a lower basic flow energy, which means that it flows better. And it worked just fine. I mean, it was incredible. So two different mixing methods. They give different structures. One has this coated structure, and one has the loose powder in there. Basically, what we found out using this mace process is what went wrong. Nothing went wrong. In fact, this was an incredibly consistent process to get the same basic flow energy almost every time that we did it. We've actually put this process in production about 2 years after we started AVEKA, and we have been in production with this process for 25 years to come up with this better flowable product. Now, this is an interesting way of adding that small amount of material at disparate particle sizes and getting a consistent mixing that really can give you a unique and interesting product. But one of the things that we were asked almost immediately, and this is about 25 years ago, was how do I blend liquids with a small amount of liquid with powders? And this is the first example that we had of this, that when somebody asked us to put less than 1% liquid on a submicron particle and develop a continuous process. Now, the challenge with this is, if I were to give each of you a cup of flour and take an eyedropper and put 1 drop of water into there, and I let you go back to your labs and mix that up, my question to you is, how long is it going to take you to uniformly mix that liquid water into that 1 cup of flour? And to uniformly blend it, I would assert that the answer is an incredibly long time. And in fact, you might not be able to do it. And the reason that you might not be able to do it is what's called a Pickering emulsion. What happens, and we've all seen this is a Pickering emulsion where you have an oil droplet stabilized in a water matrix, stabilized by particles. If you've ever seen it, when you put a drop of water in flour, what happens is many times you'll get a stabilized drop where the flour particles will stabilize that drop. This happens with many particles. You know, it's not just a water and flour, but it happened in the case where we were doing this with the particular submicron particles, is that no matter how hard you blend, that emulsion wants to keep it stabilized with these solid particles. So in the case of a standard Pickering emulsion, it's oil and water, In the case of a blending situation, the Pickering emulsion is the water being stabilized by the particle, and the continuous matrix is air. So we actually found out right away, even though magnetically assisted impact coating was used for coating particles on particles, it was equally as useful to take a small amount of liquid and disperse it across the particles. We actually end up using this to coat TiO2 for microelectronic displays that you can see here, and we've been doing this for a long time. Once again, it's back to that same process of, instead of smaller particles and larger particles, it's larger particles and a small amount of liquid. This magnetic system here with all the magnets in here operating at 3,600 RPM does a great job of distributing that liquid. It doesn't work as well with a V blender. In fact, it's terrible. Our measurement method in this case isn't a flow system, but we actually use thermogravimetric analysis to analyze the sample. And unlike the flow system, that functional property is a macroscopic property. And when we're measuring with a TGA analysis to see how much liquid we put on there, we really don't know how well it is. I mean, this is one of the real challenges, is how uniform on a microscopic level is your mixing. We believe it is very, very uniform, but I don't really have the data to back it up. What went wrong? Nothing. The process, once again, just like the powder on powder, is extremely consistent. We get great results, and we've actually been in production for 17 years making this small amount of liquid dispersed on a high surface area material, and it works wonderful. So my last example here is mixing using funnel flow. And the statement of challenge that we're gonna show you a little video here in a second is, how do you mix widely separated segregated materials during mass transfer? Because what people are interested in doing is, I really don't want to have to mix every time I put it into a bin. If I can mix in a continuous way with no moving parts, wouldn't that be great? And it turns out that I don't think that this is a new to the world method, but the method that they use to do this is taking 3 offset funnels, and you can get incredible mixing. So this is a video from 1990. This is a video that I hope you get a chance to watch all of it, because it's very interesting. It's a video from 3M that I just found last week. I was there at 3M when they made this video, but I never saw it. And this is a way that they came up with mixing powders without any moving parts. So let me run it here, and let's get to the right section in the movie.
Throughout these demonstrations, we've talked mostly about preventing segregation in materials that are evenly blended to start with. But what about material that starts out somewhat segregated? Is there anything you can do to remix these materials? Yes, there is. The results of this next demonstration may seem unbelievable, but there is no trickery here. These 3 sharply angled funnels are mounted offset to each other. This would be a good method of remixing material while recharging bins above the line. Watch what happens when we charge this funnel system with material that is as sharply segregated as you can get. We charge the top funnel with the red and the white granules in equal proportions. Notice at the bottom that the only segregation still remaining is that caused by the fact that we're allowing the material to form a cone. The triple funnel arrangement has effectively remixed the segregated granules.
So I found this very interesting. I hope you could hear the narrator talk. It's an old style video, and I call this there's something new for every old dog to learn here, even though might be old. What went wrong? This is an incredible mixing process. What went wrong is, I never knew about this until this week. I never knew about this process. The reality is, I'm going to actually be putting it in some of our plants to see how well it actually works. Because if I can do mixing without any moving parts, and just adding materials in random spots and getting them to mix in a relatively easy system like that, I need to try this out. So what did I leave out? I didn't talk about the use of mixing in pharmaceuticals, which is an incredibly important area. The pharmaceutical people spend a lot of time trying to make sure that what goes to their powder compaction to make tablets is absolutely uniform. And the pharmaceutical industry spends more time on blending than probably almost anybody else. I didn't talk about friable materials. You can't use a high shear granulator to do friable materials, but there's some opportunities for you to take a look at things. I didn't look at color control. That can be a blending process where you mix powders of different control. And I didn't talk about pastes and slurries. I mean, I talked about adding a little bit of liquid to something, but I didn't talk about pastes and slurries. I also didn't talk about batch versus continuous, other than that one discussion about the Forsberg mixer. I'd like to show you down here at the bottom. This is a continuous V blending system. This is called a zigzag mixer. We use zigzag mixers occasionally when it's necessary. This little teeny zigzag mixer, this is about an 8-inch diameter pipe, can do thousands of pounds an hour, and it's basically 1, 2, 3, 4 V blenders put together, and you pour the powder in here, and it comes out about this end, and it's an absolutely wonderful continuous system. It's something really to pay attention to. And I didn't talk about the scale up of lab mixers, but I had mentioned earlier on how much I like the Residine system and the FlakTech systems. In our lab, we have the FlakTech system. We don't have a Residine system, but both of these processes, I think we all know that these are absolutely great material or great processes to use. They're some of the finest blending processes that I've seen, and you can do 25 grams all day long, and you might even be able to do maybe a kilogram of material, but these things just don't scale up because of the high centrifugal energy and the FlakTech and the high vibration. You get limited by the size of volume. So these scale up. Be very careful about what equipment that you pick to use in the lab, because it can come back to haunt you. Let me give you some final thoughts. Oh, I call it fluid bed processing. I'm sorry. This is blending processing. Please think about some of the resources that you have. Reach out to the International Fine Particles Research Institute. This is an organization of companies talking about particle processing in all its myriad forms. There's some great consultants available. Paul Mort at the University of Purdue. He's formerly from Procter & Gamble, and he's an expert on powder mixing, along with Carl Jacob, who just recently retired from Dow and now at the University of Michigan. And I'd like to put a plug in once again for Jeff Hoffman at Paul Abbey. They make these mixers, and Jeff is a wealth of knowledge on this. The ideas for the future, for me, my take on this whole thing is, I really want to go back to the future. I want to actually look at that funnel mixing. I'm very interested in anything that I can simplify my operation, and 3 funnels instead of any kind of other blenders seems like a great idea. And finally, I would like to leave you with this idea that blending can be straightforward, but uniformity, micro ingredients, segregation after the fact, these got all big issues. The process conditions and materials and the blenders that you pick are absolutely critical. And I want you to be prepared, or want you to be prepared to be surprised, even with simple systems, even on something as simple as blending. And with that, I think I'm done. Thank you very much for listening. And Julie, I'd be happy to answer any questions.
So thank you so much for the excellent talk. I learned a lot, and I definitely would be interested to go back to the YouTube video and watch how they blend in such a smart but easy way. So it seems like quite a few people are interested in micro ingredient blending. So can you comment a little bit about efficient mixing of the fraction 0.3% of nanomaterials into microfine powders?
Yeah, I would say, really a challenge with that, because when you get into both nanoparticles and micro fine materials, typically they're going to have high cohesion. So the blending process is difficult just because of the cohesiveness of the powders. And if they're not soluble, so you can use the trituration method that Alice Wilkinson had, you know, you're really limited to how to do it. If you really have that 0.3% of a nanoparticle and a fine particle, please give me a call and let's talk about using that MACE process. I mean, that to me is the real answer to that question. I think other ways you might be able to do it, but I just think that MACE really stands out as a unique and good way of handling that.
Thank you. Can you comment on the types of segregation mechanisms and what are potential solutions to prevent or suppress segregation?
So yeah, that is a great question. It turns out that, you know, segregation is usually a function of that disparate size. I mean, that's usually what it comes down to. There's a different movement for a larger particle and a smaller particle. And so the way that people deal with that is please go and watch that 3M video, because they had special ways of handling the material. It's really kind of beyond what I would have here to say. But the reason that the pharma industry does agglomeration is to bind all the particles together so you have one big particle, all the same size, with a mixture of components, and so you minimize that segregation. So it's that Brazil nut effect, and people either get around it by handling the flow of particles once they start moving, or they agglomerate to actually solve that problem.
Thank you. So in your slide, you mentioned about fume silica. How do you control fume silica addition without dusting?
Without dusting?
Mm-hmm.
Yeah, that's a great question. That goes back to those, you know, if you're going to use a lot of fume silica, the best way to do it is to have those bag dumping stations, because if you don't have it, it's just everywhere. I mean, that's the real problem. It's bag dumping, and then having really good airflow in your room, because you will always get a little that floats around. So it's a tough one.
Thank you. Can you recommend some tutorial or references for analysis metrics of a blending process?
Wow. You know, I would actually push you towards the Paul Mort reference and the Carl Jacob. This is this characterization, it's always a tough one, but those two guys I think would really be a great place to start.
And so that said, the slides will be posted onto our website within a week's time. So in the slide, you can then get to the contact info, or you can email us at labinfo@horiba.com. We would love to take that question offline. Okay, how variable is your product drum to drum, and how do you measure this?
Yeah, that's always the question, right? The best that you can do is sample and sample and sample and sample. You know, do a thief on the material and take it out. And now you're looking at, is it the right color? Is it, you know, can you sieve screen it because you have different particle size, and see what that is? There isn't this standard method that you can just, you know, wave the wand over it and you know that it's the same. You're almost going to have to develop your own techniques, and it's usually your sampling protocol and then a particle size measurement. If you can do that, that might be the easiest thing, or a colorimetric measurement. But, you know, at the end of the day, it's the challenge that we all have on how uniform your product is, and measuring that. Sorry, I wish I had the secret answer that I could give you.
Well, blending is never as easy as it appears.
That's
There we
right.
go.
That's exactly right.
Okay, I see one more question that came in. is there a way to minimize the particle size and shape change in a high-intensity mixer, Henschel style?
To define it, is that what it was? To define that
To
to
minimize the
measure?
particle size, minimize the
To
change in
minimize the
particle size
particle
and shape.
size change.
Hmm.
Yeah, yeah. Hmm. You know, obviously it's going to be very material dependent. If you have soft particles or if you have friable particles, I don't think a Henschel is maybe the right answer for you. I would really consider if you can get out of that to use something that has a little bit more energy than a Henschel mixer. But having said that, you might be into that available equipment dilemma problem, and I guess wow. I guess I would actually have to see the materials and understand it before I could give you any input on that. You know, those high energy processes, they're just made to change things in there. So I guess I don't have a good answer. I apologize. I'm worthless.
No way. These are really good questions, though. I think this is why this webinar, just specifically on blending, is so well received. Um, just one last question, and I do want to honor your time. How do you mix, I think it's silane additives to TiO2, to titanium dioxide?
So organosilane additives to TiO2. We
Hmm.
use that MACE process. That's exactly what we use. We've never found anything as good as that to do the mixing. And we believe, once again, hard to measure it, but we believe with all the measurements that we had, thousands and thousands of them over the year, that that's about the best way to do it.
Well, thank you. Thank you so much, Willie. Well, I think that's it for today. Thank you so much for the excellent talk. And on behalf of our group, thank you so much for attending, and we'll see you at our next webinar. Don't miss it. Thank you so much, Willie.
Thank you.
Thanks, everyone. Bye now.